Okay, welcome to lecture. We'll continue in just a second, talking chapter 14, kind of where we left off last time. So we should be just around here where we are talking about buffers. All right, so let's get started. So a reminder as well, again, if you have questions, feel free to type them as we go along. And again, I'll get to your questions, even again, if we happen to pass it. So last time we were lecturing, we got into, we talked about polyprotic acids and how to do the calculations involving them. Remember that when an acid has more than one H plus that comes off, essentially the majority in most cases of that H plus that comes off will come off in that first sort of dissociation, as each of the H pluses do come off one at a time. And as we saw in that problem we worked out, you essentially, if you need to calculate the pH of a polyprotic acid, in most cases can do it directly from usually the first H plus concentration, because as we saw, as we went from the first H plus that came off to the second to the third, essentially the H plus concentration really did not change all that much from the first dissociation. So usually almost a safe bet if all you're asked for is the pH is to just do it based off of that first H plus that comes off. Remember, since they do come off in a stepwise fashion, there is a Ka value for each of those H's that come off. And obviously you would want to use the appropriate one. Then we started talking about common ion, and a common ion is a solution that, much like the name implies, contains something that will set up an equilibrium, usually. So some type of weak acid, perhaps a weak base, and a salt or something like that that will provide an ion that's in common with that weak acid or base, for example. And that's going to suppress the dissociation of that weak acid or weak base. Again, based on Le Chatelier's principle, by supplying that ion that's in the solution with it, it essentially will cause the equilibrium basically to shift to the left towards the whole weak acid or weak base, and it's going to keep it together and not allow it basically to break apart. So we saw an equation that you could use for that, which is the Henderson-Hasselbalch equation. Again, that is our pH equals the pKa value plus the log of the base concentration over the acid, where the pKa value is equal to minus the log of the Ka. And that's the Henderson-Hasselbalch equation. That's really, as we're going to talk about right here and kind of pick up with, what is used to calculate the pH of really a buffer solution. And a buffer solution really is a common ion effect that's happening. Now, that equation that we see up there as well is the one that most people obviously will use for the Henderson-Hasselbalch equation. And you can use this equation for both acidic or basic sort of conditions. And you'll get the right answer as long as, again, you take the base on top divided by the acid and you use the pKa value. Now, there's also sort of a version of this equation, much like when we have pH, we also could calculate pOH. And there is sort of a version of this equation where you could calculate what's known as the pOH, obviously. And you can use it for a common ion sort of problem. You could also use it with a buffer type problem. That's more of a basic buffer. But again, you get here the pOH would equal what is known as the pKa. I'm sorry, my bad. Grab an eraser here. Take two there. Would equal, I'm sorry, the pKb, not A, B, since we're dealing with the base, plus the log of the acid over the base, where here the pKb value would be minus the log of the Kb value. So this one, sometimes people will use in sort of a basic situation, and later on when we're talking about buffers here, sometimes people will use that for a basic buffer. And there is a nice relationship, kind of like pH and pOH. So let's put it over here. If you take the pKa value plus the pKb value, that actually will equal 14. So kind of like pH and pOH, pKa, pKb, you could kind of equal it to 14 as well. So you could kind of quickly get the pKb value if you needed from the pKa and vice versa. Now, you definitely can use the pOH equation up here, but you do have to remember that things are reversed from like how you normally would think about it. And again, this is going to give you only the pOH, which means you would still need to subtract 14 from it. And in most cases, in problems like buffer problems where you would probably apply this, for example, most of the time they're not asking for the pOH, they are asking for the pH value. So my recommendation is, although you may see these equations here and you absolutely could use them if you want, I would stick with the Henderson-Hasselbalch equation here for both acidic, basic conditions, really any conditions, because probably 9 times out of 10, again, what you're asked to solve for is the pH. So that equation there, the Henderson-Hasselbalch one, the pH equals pKa plus the log of the base over the acid, that's going to most likely give you the answer you're looking for kind of directly without having to remember, oh, the other one gives me the pOH and I still have to subtract 14 to get to the pH. So again, you could use either one. And sometimes people do use the one on the right there with the pOH, again, for more basic conditions, basic buffer conditions, those type of things as well. Okay, so let's then talk about a buffer, which is essentially sort of where we left off. And a buffer is a solution that basically contains a couple of things. It can either be a combination of a weak acid and its conjugate base. So one combination for you to make a buffer would be a weak acid and its conjugate base. And sometimes that's referred to as the salt of its conjugate base. The salt part just means essentially they put something on that salt that has a negative charge, probably a sodium, a potassium, something like that. Or you can have the opposite sort of thing. You can have a weak base and its conjugate acid, or the salt of its conjugate acid. Also, same deal. They probably just put something there to balance out the charge, which is what makes it a salt. The salt, again, is just an ionic compound, like we saw before. Now, the important thing about a buffer is a couple of things. Both of those things are in the solution to begin with. So you have both the weak acid and the conjugate base, or you have the weak base and the conjugate acid in the solution to begin with. And that really, as we'll talk about here in a second, is what gives a buffer the ability to kind of work correctly. And what a buffer is a solution that has the ability to resist changes in pH, even if you add some more acid or base to that solution. So what we're talking about here, and what sometimes people, I won't say mess up on, but sort of mess up on when they think about buffers, is they do think about buffers as being a neutral solution. So they sometimes think buffer, oh, that is a neutral solution. And it's really not a neutral solution. You could make a buffer that is neutral with a pH of 7. You could also make a buffer that has a pH of 4. You can make a buffer that has a pH of 8. What a buffer is a solution that whatever pH it starts at. So let's say we made a buffer solution at a pH of 4. When you make that buffer solution correctly, and then you add either acid or base to that buffer, the pH will remain around 4. Will it go up? Will it go down? In reality, it will go up. It will go down a little bit. So if you were monitoring sort of the pH with the pH meter, you would see a change in the pH when you add acid, which would make it go down a little. You would also see a change in the pH if you added base. It would go up a little. But what a buffer is able to do is prevent big changes in pH. So for example, if I started my buffer at a pH of 4 and I add base to it, perhaps the buffer goes from a pH of 4 to maybe like a pH of 4.1, 4 point something, it stays in that 4 range. But if I add that base to something that is not a buffer, it would go perhaps from a pH of 4 to like a pH of 12 or a pH of 10, a very big jump in pH. So what a buffer is able to do is basically maintain the pH where it's at without these really large changes sort of in the pH of that solution. But it really will go up and down a little bit, but not a ginormous amount. So let's just talk about really how a buffer works. We'll come back to this in just a second here. All right, so let's first take a look at sort of what happens when we put a strong acid, an acid or base in a non-buffer situation. So let's just say we add an acid or base to water. Water is not a buffer. So if we add some acid or base to water, so for example, if we take some hydrochloric acid, which is a strong acid, and we add it to water, what's going to happen is it's going to break apart into H plus and Cl minus. And it's going to 100% break apart into these guys, as we talked about, as it's a strong electrolyte. It's going to 100% break apart. And we would definitely expect this guy to be acidic. And we would definitely expect the pH of water, for example, if the pH of water was, say, 5 to begin with, we would see perhaps a drop down 2 or so. Again, just making up the numbers, but we see a pretty good drop, in terms of the pH, maybe even lower depending on the concentration that you add. But we would expect the solution to be acidic, and really because in water, what it has generated is a lot of free H plus. And remember, it is that free H plus that affects the pH of a solution, right? Minus the log of the H plus. That as the H plus concentration goes up, the pH will go down. And vice versa, right? As the H plus concentration goes down, the pH will go up. And that's because the concentration of H plus and OH minus are opposites of each other. So as one goes up, the other goes down, and vice versa, right? So this guy then goes down, this guy will go up. So when we add hydrochloric acid to water, which is not a buffer, it's going to 100% dissociate. It's going to produce a bunch of free H plus really quickly. And thus the pH we would expect to be a pretty good jump in pH. Again, it may even go lower than 2, for example, and just made up those numbers, but pretty good jump there in terms of pH. Now, if we took water, which again is not a buffer, and we decided to add a base to it, something like sodium hydroxide, When we add sodium hydroxide to water, again, because it's a strong electrolyte, it is 100% going to break apart into sodium ions and hydroxide ions. And same deal here, 100% of what we got going on is going to be these ions. And that means just like kind of above, although we didn't generate H+, we made a lot of free OH-. And by making a lot of that free OH-, because OH- is tied to H+, what that means is the amount of OH- goes up, the amount of H- is basic. So again here, perhaps the pH of the water was 5-ish. You add some strong base to it, maybe it actually jumps to like a pH of 12, 10, 12, something like that. A pretty big jump in pH. And that's because, again, water is not a buffer. So essentially, when you add a acid or base to it, you're essentially increasing the amount of free H+ and OH- very quickly, and thus making a very big sort of change in the pH. Now, let's talk about sort of a buffer and what happens with a buffer. So in a buffer situation, again, we have that combination of a weak acid and the salt of its conjugate base. Or again, we have a weak base and the salt of its conjugate acid. And again, in this solution to begin with, you have your weak acid, for example, floating around. And you have the conjugate base floating around. So you basically have an acid part in that solution. You also have a base part floating around in that solution to begin with. Or again, obviously, you could have the opposite, a weak base and a conjugate acid. And why it's important that these guys are weak is because when we have a weak acid, so for example, when we have something like acetic acid, which is a weak acid, when we put something like acetic acid into solution, it is going to set up an equilibrium because it is a weak acid. So in solution, by having that acetic acid, it will set up this equilibrium. And because it's able to essentially set up this equilibrium in the solution, that is essentially what allows us to have both of those things in the solution at the same time. Because once it sets up this equilibrium, you will have some of this in that solution, and you will have some of the acetate as well in that solution. And again, that's what's really going to allow it to act as a buffer, is the presence of both of those guys in that solution, to begin with. If you took something like ammonia, right? And ammonia is a weak base. Its conjugate acid would be NH4+, right? So these two guys also able to set up this equilibrium here. And we will have, perhaps say it's ammonium chloride or something like that. This would be our weak base and our conjugate acid, right? And again, I would allow both of those guys to be in that solution to begin with. And this is why a buffer has to be made up of those things. It has to be made up of a weak acid or weak base, because when we take a strong acid, like we have above actually, or a strong base. So for example, like our HCl that we had above, when it's in solution, there is no equilibrium set up. And what that means is really in solution, you no longer have an acid part. You have really just the conjugate base part, which means if you took a beaker of that stuff, you essentially just have this guy flying around with your H plus, right? And since this is a neutral salt, this H plus here obviously is going to have a drastic effect on the pH like we saw above. So that is why you cannot have a buffer that is made up of a strong acid or a strong base. It does has to be the weak acid or weak base, because that's going to essentially set up in that solution an acid part and a base part. So that will essentially, like we had, set up yourself an acid part that's in that solution and a base part. And that's really important for how a buffer is essentially able to maintain the pH, because it has both of those parts in there. So first major thing about a buffer, again, is it must be a weak acid or a weak base with its conjugate partner to be a buffer. You cannot have a buffer that is made up of a strong acid or strong base. Now, with that part of it, I will say this, that you can make a buffer from a strong acid or strong base, but once you've made the buffer, the strong acid and strong base will be gone. And we'll see some examples of that as we go through some of these calculations. But you technically can make a buffer from a strong acid and strong base, but it technically is not a buffer until really those strong acids and strong bases have fully reacted and are gone. So, you may see somewhere where we're talking about buffers that you can make it from a strong acid or strong base, but the buffer itself is ultimately, when it's all made, no longer a strong acid or strong base. It is a weak acid and a weak base that is there. And again, later on, there's some calculations where we'll see sort of how that develops, and I'll kind of point it out to you. So above here is what we have going on when we add an acid or base to just water, for example. That's not a buffer. We expect a pretty good jump in pH. So let's say, for example, we added a acid and base to this guy down here, this buffer. So take a look at that on this page. So let's say we added the exact same acids and bases to a buffer. And for us, we will use, why not the classic everybody uses, we'll use acetic acid and sodium acetate. So again here, acetic acid is a weak acid, and sodium acetate is its conjugate base. And again, that is your basic buffer situation happening. The guy on the right there would be the salt of his conjugate base, and really what makes it the salt part is the sodium. And truly, the sodium is really not doing anything in this reaction. It's a neutral salt. It's not going to affect the pH. So, I mean, if you want to kind of write it down to just the basics, these are really the two parts of the buffer that are going to be participating here. So it's really the acetate part that comes from the sodium acetate, and it is the acetic acid that is truly what's going to, like I said, participate here and really affect how the buffer works. Again, you could leave the sodium in if you want. It's not going to really affect anything like we talked about earlier. Again, sodium, a neutral salt, so will have no effect on the pH. So let's take that same strong acid, HCl, and let's see what happens when we do add it to our buffer. So as I mentioned before, what really allows a buffer to sort of work correctly is the idea that in the solution, we have acetic acid, which is an acid part, and we have acetate, which in this case is the base part, right? So we have both of those things floating around in that solution. So when I add something like HCl, which is hydrochloric acid, because it's an acid, it's going to react in this case with the base part of the buffer, right? Because the reactions are called acid-base reactions. So the acid-acid reaction doesn't occur, right? So we're going to have the acid that we're adding react with the base part of the buffer. And when that reaction occurs, we would have HCl, which is what we're adding to this little beaker of a buffer. It is going to pick, I don't know if it really picks, but it's going to pick the base part of the buffer, which is our acetate. And when that reacts, we will get acetic acid. It's really a double displacement reaction. And again, if you left the sodium in there, you would get sodium chloride. So if you want, I'll leave the sodium in there so we can see it. So you don't wonder where it came from. And again, you could take the sodium out and not put it in, or if you want, you could leave the sodium in there. And this really is a double displacement reaction, right, that's happening. So we're just switching out and we get these guys. So we do see a couple things that are different than when we saw when we added the HCl to water. First off, and this always happens, we actually made more acetic acid, which if you remember was part of the buffer to begin with. And that always happens when you add an acid or base to a buffer. It will use up some of the buffer, one part of the buffer, but it will generate some more of the other part of the buffer. So clearly acetic acid was there to begin with. That is not going to have any sort of effect on the pH too much. We also are left with this guy over here, which is sodium chloride. And from our talk about salts, we should know that this is a neutral salt, which means it also is not going to have any sort of effect on the pH. But more importantly, what we do not see on the right-hand side in this equation that we do see on the last one where we added it to water is when we added HCl to water, we generated a whole bunch of this free H plus. And it really is that generation of the free H plus that is going to make the pH jump a lot, because you just introduced a lot of free H plus by itself into that solution. As the H plus concentration goes up, as we talked about, the pH should go down. Now, if we look at that HCl and what we're just doing here, the important thing is when we look on the right-hand side, we actually do not see any free H plus that was formed. And again, it's the free H plus that really affects the pH. So because there was no free H plus formed, no free H plus, that should mean that the concentration of H plus will remain relatively constant. And if the H plus concentration remains relatively constant, that also means that the pH should remain relatively constant as well. So the way a buffer is able to prevent the change in pH here when we add an acid is all that free H plus that normally would be just let go free into that solution really gets sort of gobbled up and incorporated into making acetic acid. And the key here is we did not generate a lot more free H plus. H plus remains relatively constant. The pH will also remain relatively constant. What I mean about relatively constant is, again, if you were monitoring the pH of the system, let's just say the pH started at 4.74, and you added some HCl to it, you would actually see the pH go down. But perhaps it goes down to 4.69, it hangs right around that kind of 4.7-ish number where it began. It's not going to go tremendously down. Again, it wouldn't go from like 4.74 all the way down to a pH of 2 or 1 or something like that. It's able to pretty much maintain its H plus concentration. Remember, although this is not generating a lot of free H plus, we are sort of increasing a little bit of acetic acid there. So it will provide a little bit of some H plus, and that's why you will see the pH go down a little bit. And it should go down obviously in the correct direction, which in this case would be down because we're adding HCl. Any questions on that? So let's also look at what would happen if we added that same base to this buffer. So if we added our sodium hydroxide to our buffer, again here, when the sodium hydroxide, which is a base, will act with the buffer, it's going to act with the acid part of the buffer, right? So we get that acid-base reaction that occurs. So the reaction that's going to occur is the sodium hydroxide will react with the acid part of the buffer. And here you're just going to get a acid-base sort of reaction that's going to occur, and we're going to generate water and a little sodium acetate. And in this case, again, when we look on the product side, we have generated some water, which again is not going to affect the pH. And we also see that we generated, again, more of the sodium acetate, which was essentially part of the buffer to begin with. And as I mentioned before, that is always what happens with a buffer. You pretty much use a little bit of one part and you make a little bit of the other part. So that also, because it was part of the original buffer, is not going to have a drastic effect on the pH. Again, just like the last one on top, if we look back to when we added the sodium hydroxide to water, the one thing that is missing on the right-hand side when we did it to the buffer is we did not produce a lot of free OH minus in this case. So when we added that sodium hydroxide to the buffer, sodium hydroxide to water, which is not a buffer, we generated a lot of that OH minus. And again, that is essentially what kind of triggered this effect over here that triggered the OH minus spiking up, which would trigger the H plus concentration coming down, and that triggered the pH jumping a lot because of that sort of chain of events that occurred. And when we look at when we add that exact same base to a buffer, again, we see on this side no free OH minus is produced. And it's the same logical thinking as sort of above. Because we have no free OH minus is produced, the OH minus concentration is relatively constant. And because that is relatively constant, that would also keep the H plus concentration relatively constant. And because the H plus concentration is relatively constant, that should keep our pH relatively constant. So our pH would be relatively constant as well. Again, just like above, if you were monitoring the pH of the solution, you would see it go up. So again, if it was 4.74 pH to begin with, you added this base, perhaps maybe it goes to 4.8-ish or so, it will go up a little bit. It's not going to, again, jump from like 4.7 to a pH of 10 or 12 or anything like that. So it'll be this sort of gradual increase in pH, but not a tremendous jump in pH. And that is again because we did not produce any of that free OH minus, and that essentially will keep our H plus concentration constant, are relatively constant, and it should keep the pH relatively constant as well. Any questions on that? So essentially, a way a buffer works, or how a buffer works, is because it does contain both a acid part, which is a weak acid or conjugate acid, and a base part, which is a weak base or conjugate base, and they're both in that solution together. Because you have a weak acid or weak base, it's able to set up that equilibrium, which will keep those concentrations in that solution and keep the acid part and base part in. That when you add an acid, it will use up a little bit of the base part of the buffer and make more of the acid part, and vice versa. When you add a base, it will use up a little bit of the acid part of the buffer and make some more of the base part of the buffer. But the ultimate way a buffer is able to maintain the pH is it really does prevent the production of free H plus or free OH minus in those solutions. And by keeping those concentrations relatively constant, it by in turn keeps that pH remaining relatively constant. So just to visually sort of draw it out, if you will, if you had a buffer and it will have an acid part, it will have a base part, and if this is our buffer. And if we make this buffer, a lot of times when you do make the buffer, we do oftentimes will make it sort of equal parts. A lot of times keep the acid part and the base part relatively equal to each other in terms of their concentration. So if I add an acid to this buffer, a different acid, what's going to happen is it will use up some of the base part, as we saw before, and it will make some of the acid part. So I'll just draw it a lot bigger. I'm not sure why. Not to scale, obviously. So the acid part would increase, and the base part would decrease for the buffer as the reaction would go through. And vice versa, if we added to that buffer a base, the base would react with the acid part and use up some of the acid part. And what we would see is the base part of the buffer, again, not really drawn to scale, would increase, and the acid part would decrease. And this is why a buffer could kind of work if you make sort of the correct buffer and with the correct sort of molarity and so forth, concentration. This is why a buffer can sort of maintain that pH over sort of a long period of time because it's, sort of self-generating. It generates one part of it, it uses up another part. This is also why there's something that is referred to as buffer capacity. So let's just say, for example, you didn't follow the instructions, the directions. I'm sure you wouldn't do that, but maybe you were not paying attention and you decide, I don't remember how much acid it said to add to this buffer. I'm just going to keep adding acid. So let's just say you just keep adding acid. To this buffer. What's going to eventually happen is, right, the base side here is going to continue to get smaller and smaller and smaller until at some point, to exaggerate, that's all you got left of the base part over here. And at some point, you're going to blow through sort of the base part of the buffer. And it will no longer have that base component to maintain basically a buffer or to maintain the pH. Yeah, so the question is when we talk about adding an acid or base, usually it's a strong acid or base. Technically speaking, you could add the other as well, a weak acid or base, but usually, for example, if you go make a buffer, if you made a buffer solution, usually when you make a buffer, even if you sort of measure out everything as correctly as you can to make the buffer, usually your pH won't be exactly maybe where you want it to be. So usually a lot of times you will use a strong acid or strong base, and you actually can use it to adjust the buffer to exactly the pH that you need. So for example, if I were going to make this acetic acid buffer, um, and I wanted it exactly at a pH of 7.4. When I made it, perhaps the pH to begin with, after I mixed everything together, was like a pH of 4.69, for example. We used the number up there. And like, well, I don't want to start at 4.69. I want to actually start at 4.74. So you can actually dial in the pH of your buffer by slowly adding, in this case, some sodium hydroxide, right? Some strong base, and it will kind of slowly bring that pH up to exactly where you want to begin with at 4.74. But usually, in terms of a buffer, the acid and base that you're adding usually is a strong acid or strong base, is usually what you're going to add to that. But technically, you could add some weak stuff, but it will then kind of mess up perhaps some of the equilibrium and may set up some new equilibriums. So usually it's a strong acid and strong base that you add kind of to it. All right. So if I happen to just keep adding the acid to this buffer, eventually it will use up all of the base part. And really what you'll be left with is just the acid part and of the buffer. And then if you continue to add acid to it, at that point, there's nothing in the buffer to prevent the dreaded free H plus spin from being formed. So when you would keep adding that strong acid to your buffer, and if you happen to have used up all of the base part of the buffer, at some point you will start generating some H plus. And it's at that point where you would see a big jump in the pH. It would go down a lot at that point. So there is sort of a buffer capacity. It has to do with the concentrations of the weak acid and base that are in there, or the weak base and conjugate acid that are in there. The concentration is really important as well. For example, if your buffer here was, say, 0.01 molar, and you didn't read the instructions, instead of grabbing like the 0.1 molar hydrochloric acid, you grabbed like the 18 molar hydrochloric acid. When you would add that 18 molar hydrochloric acid to it, depending on how much you added, there would not be enough of the base part of the buffer to handle that. And you would essentially blow right through the base part of the buffer, and you would end up in this position very quickly, and you would actually see a big jump in pH. So the molarity of the strong acid or base, for example, that you're adding to the buffer, and the molarity of the buffer itself is really important in how effective a buffer can be. So just because you say you made a buffer and you add some acid or base to it, it may not be able to work correctly if the molarities are really different. Because ultimately, what we'll talk about in just a second is what makes a buffer able to sort of work is the ability to have a certain amount of that weak acid in there and a certain moles of the weak base in there, or conjugate base in there, to react. But if you add way too much, it will blow right through it. So there is a thing known as buffer capacity. It is really based on the molarity of the buffer, and also obviously the molarity of what you're adding. And usually when we make a buffer, a lot of times, how do you know what's a good buffer to make, or what is a good choice of perhaps a weak acid and a conjugate base, or a weak base and conjugate acid to choose to make a buffer? And you actually can use the Henderson-Hasselbalch equation, which again really is the equation that we use for buffers. So this really is, our buffer equation. This is really our buffer equation here. And if you make the concentration of the base the same as the concentration of the acid part in the Henderson-Hasselbalch equation, that would give you the pH equals the pKa value plus the log of 1, if they're equal to each other, right? And the log of 1 will equal 0, which means when you're trying to select perhaps a good weak acid or a good weak base to make a buffer from, usually we go plus or minus 1 of the pKa value, because if you keep the concentration of the weak acid and conjugate base in the buffer basically the same, or you make it the same sort of concentration, what that means is the pH will equal the pKa value. So for example, if I wanted to make this acetic acid buffer, which is a pH of 4.74, I would choose acetic acid, would be a great buffer for it. A bad choice would be something like ammonia, which is ammonia and ammonium chloride or something like that, because the pKa value, for example, for ammonia or NH4 plus is like 9.25 or 9.35, is in the nines. And that, although you technically could probably get the buffer to be made, it's going to require a lot of extra stuff to be added in there. And it's really not going to be as an efficient buffer as choosing acetic acid, which has a pKa value of 4.74. And that means there's going to be very little adjustment that you would have to make. So sometimes you're asked, and in the buffer lab, which will be coming up next week, I think, we will be asked to basically choose a buffer or what you should make the buffer out of. And when you're trying to choose what weak acid conjugate base combo is good or what weak base conjugate acid combination is good, what you want to look for is the pKa value that is close to the pH of your desired buffer. So you want to choose something where it has a pKa value very close to what you're trying to make. Any questions on sort of buffers and sort of in theory how buffers actually do work? So again, a reminder, if you say a buffer is a neutral solution, technically that is wrong, because again, you can make a buffer from pH of 0 to 14, anywhere along there. Again, what a buffer is a solution that once you made it, has a particular pH associated with it. And even if you add some strong acid or base to that buffer, it should be able to maintain the pH where it started at. And again, as we talked about, you will see a little bit of a rise or lowering in pH depending if you add acid or base to it, but you will not see these tremendously big jumps in pH. Any questions on buffers fundamentally, how they work? Okay, so then let's talk about actually calculation-wise, sort of how buffers works. And in just a second, we'll get to that. So, and that is essentially what we were seeing here. Just to come back to this slide, this is what we were talking about when you add an acid, a strong acid to a buffer. Again, going to react with the basic part of the buffer, going to produce the acidic part of the buffer. And thus on the bottom there is where we add a base, strong base to the buffer. It's going to react with the acid part of the buffer and again make the base part. So that's why, again, a buffer is sort of able to maintain that pH over a long period of time, because in the process of reacting, it's essentially kind of regenerating some parts of the buffer to begin with. All right, let's go this away. And here's just a graph of demonstrates that again in water, which is not a buffer solution. We do see this tremendous drop very quickly in pH. Again, it started up there about 7-ish. It ended down at 2, so a pretty big, and even ended at 1 as you kept adding all the way down the road there. A very big jump in pH, which would definitely tell you this is not a buffer, as opposed to the buffer there. You can see it pretty much maintains a very constant line across in terms of pH. It doesn't go up, it doesn't go down. In reality, like I said, if you had a pH meter and you were monitoring it and you added acid to this buffer, you would see it go down. But again, you wouldn't see it go down tremendously or a big giant jump in pH. So let's first talk about each of these. Are each of these a buffer solution? So take a moment, take a look at them, and then we'll talk about if these are buffers or not buffers. All right, so let's take a look at this. So first thing, remember that in order for it to be a buffer, we need a combination of either a weak acid and its conjugate base, or a weak base and its conjugate acid. So when we look at the first one, A, we have KF and HF. And really the way you can determine it is if you look at HF, you hopefully could recognize that that is a weak acid. And when that breaks apart, it would break apart into H plus and F minus. And that is essentially what KF is, right? Is this conjugate base. So A would be a buffer. Yes. So you can make a buffer out of that. Again, the K here is what it makes it the salt of its conjugate base. The potassium, which is a neutral salt, is really just there to balance out the charge on the fluorine. Again, not participating really in anything in terms of a buffer, but oftentimes when we go get things, we get them in a sort of their salt solution. So, it'd be like potassium fluoride. B, if we look at it, we got KBr and we got HBr. Also, these guys are related to each other. That's HBr would break apart into H plus and Br minus. So we do have a base, we do have an acid, but the key is we want to look at this to determine, is it a weak acid? And the answer is no, it's not. It's actually a strong acid. Remember, this is like a group 7 acid. And going down in group 7, acid strength increases. So because this is a strong acid, this cannot be a buffer like that. Because what's going to happen is exactly what I wrote here. When you have that HBr in there, it is 100% going to break apart into these ions. Which means in terms of a buffer, if you remember, you need to have the acid part in there and you need to have the base part floating around. This would only provide you the base part, which will not make up a buffer, which means if you add an acid to this, it will react, but it will just continue to add basically more H plus to that solution because there won't be much of a reaction that occurs. So again, buffer cannot be made up of a strong acid or a strong base. They do have to be weak acids and weak bases. And lastly, we do have basically hydrogen carbonate or bicarbonate and carbonate, which again are related to each other by 1H plus, and that is a weak acid. And this would then be a buffer, like the buffer you have like in your blood and all that good stuff. Any questions on identifying buffers? So as I said before, the buffer itself cannot be made up of a strong acid or base, not to be confused with something we will probably see a little bit down the road, that you actually can make a buffer from a strong acid and base. The difference is, in that situation, the buffer itself, once it's made, as I mentioned earlier, the strong acid and strong base are gone. Yeah. So let's take a look here. And what I mean by that, for example, is just to kind of quickly sort of show you that is, so let's just say you took a strong acid like hydrochloric acid, and you reacted it with, say, some sodium acetate. When that reacts, it is going to make, like we saw on the other slide, some acetic acid and some sodium chloride. Sorry, I'm running out of room. Now, if you do this in a way where the starting amount of this guy gets completely used up as a result of this reaction, almost like it's a limiting reagent, like you kind of keep this guy as a limiting reagent. By the process of this reaction, you are going to, when it all hits equilibrium, have generated some sodium acetate that was there originally, and you're also going to generate some acetic acid that's going to be there as a result of this reaction. And if you do this reaction in a way where all of this gets used up, really when it reaches equilibrium, the two things you will have left will be these two guys, which is acetic acid, which is a weak acid, and sodium acetate, which is this conjugate base. And by using a strong acid and a conjugate base, you actually would be able to generate a buffer. The buffer itself, though, in this situation is just the acetic acid and sodium acetate. It is not the HCl. Although we use the HCl to make it, all the HCl was used up in the process of making it, and you were able to generate a buffer from this reaction. Same thing if you added sodium hydroxide, basically doing this reaction here. If you did this reaction in such a way that all the sodium hydroxide gets completely used up, you would have generated this buffer if you just started with acetic acid by itself and sodium hydroxide, not a buffer to begin with, but started with sodium hydroxide and acetic acid. And if you used up all the sodium hydroxide, you would be left with this buffer here, basically being made. So again, you can sort of make a buffer from a strong acid or strong base, but that strong acid and base is completely used up when it's all said and done. Any questions on that? Okay, so let us actually now get to some actual calculations here, and we'll go through this one here together to talk about it. So here we want to calculate the pH of a buffer system that contains 1 molar acetic acid and 1 molar sodium acetate. We want to know what is the pH of that just to begin with. And then when we want to know is for part B is what is the pH of a buffer system after we add some hydrochloric acid to it. In this particular case, and it's not always the case, but in this particular case, we're going to assume that all the volumes for everybody is just going to remain 1 liter, okay? And that's not always the case, and we'll talk about sort of the differences there in just a second. The Ka value for acetic acid is 1.8 times 10 to the minus 5. So let's start with part A and sort of look at it. So in part A, we have 1 molar acetic acid, and we're going to combo it with 1 molar sodium acetate. And they gave us that Ka value for acetic acid of 1.8 times 10 to the minus 5. So we can see that this is a weak acid from the Ka value. We also see that, again, the acetate part here is conjugate base. So that automatically should scream to you buffer. And again, if it does sort of scream that to you, it should probably also scream this equation to you, that the pH equals the pKa plus the log of the base over the acid. Again, our Henderson-Hasselbalch equation here, where again, the pKa is equal to minus the log of the Ka value. So as we talked about when we sort of introduced this equation, there really is two ways you could solve these problems. You could do an ice table. And if you did the ice table, it would be the weak acid here that would be dissociating into H plus and acetate. Initially, we would have not one, zero, one of this. We would have zero. And as we talked about last time, because this is a buffer, the guy right here, initially, you actually do have some acetate and is supplied by the sodium acetate. So again, when people do this table, oftentimes they screw up right there. They put zero there because they're so used to putting zero and that's location for everything else. But if you put zero there, like we talked about last time, this is no longer going to be a buffer. This is going to be just a weak acid, a Ka problem. So very important if you choose to do the table that you do have an initial concentration for that guy. Change is going to be minus X, plus an X, and plus an X. At equilibrium, we're going to get 1 minus X, X, and 1 plus X. This would obviously go into our Ka expression. You would do a little solving for X, which would get you the H plus concentration, and that would get you off to the pH. So again, this is one way you could do it. The easier way probably would be, again, if you recognize that this is a buffer, you actually could go directly into the Henderson-Hasselbalch equation, where the pKa value here would be minus the log of the Ka. That's going to give us 4.74. And then our pH would equal 4.74 plus the log of the base, which again, this is our acid, right? And this is our base. So it would be, in this case, 1/1, which is going to give us 0. And that means that the pH of the solution would be 4.74 to begin with. And again, if you went through this whole process, you should get there as well. So you can see it will be probably a little bit more work to go through that ice table, but you absolutely, if you're more comfortable doing the ice table with buffer problems, you can do them. Or you can go into the Henderson-Hasselbalch equation. So as we talked about last time, again, the Henderson-Hasselbalch equation is strictly for really buffers. So that's the only time you can use it. Other times you do need to do ice tables. But if you want to use an ice table for this, you can. Again, it's just a little bit more work probably, but it should give you the exact same answer. Any questions on part A? So part A is just a straight old buffer type problem. Here we're going to now take this buffer that has an initial pH of 4.74, and we're going to add some acid to it. And just double check, 0.1 molar HCl. So let's talk a little bit about an important aspect of these calculations, definitely here with buffers, and also later on here when we do some titration problems. What happens, for example, to the molarity when we increase the volume of a solution? I think we might have talked about this earlier as well in an earlier lecture. Because molarity is technically moles of solute divided by liters of solution, when we do increase the volume of the solution, which occurs when you pour two things together, basically, right? When you basically do a dilution or anything like that. What we see is the bottom part here starts to change. And that means if we're doing something where we're kind of constantly adding volume, for example, in a titration, you constantly add volume as you're doing the titration. In a buffer here, if you took some solution and you're adding drops of solution, acid or base to it, or pouring volumes of acid or base into it, you're constantly changing the volume, which means that the molarity will constantly change as you do it. The one thing that will remain the same is if you're just adding some more volume, the moles of the solute will remain constant though. And again, just sort of a bad drawing of this, so I'll give it a go. Again, if you had, say, 4 circles in here, those 4 circles would represent the moles of solute, right? And really, when you do a reaction, it's really these moles of solute, for example, that are really the only things available to do a reaction. So if I decided to add more volume to this, so added something else, more volume, what's going to happen essentially is, your beaker's going to get bigger. You're going to add more volume, but still floating around in there from our original sort of solution is still our same 4 circles, if you will, of solute that's able to react. The only difference is we changed the molarity because we kind of did a dilution. But if in terms of reacting, it is really just like it was before we added anything. We have these 4 guys that's able to react. We still have these 4 guys that's able to react, but there's a lot more kind of solvent and other stuff in there. But the moles of solute will remain constant. And how that relates to buffer problems and titration problems is whenever you're adding volume. So if you take a buffer like we're going to do in part B and you add volume, some acid or base to it, or if you do a titration, which you're constantly adding volume, you should always do an ice table in moles. And you want to do it in moles because, as you can see in the little picture on the bottom, there is only a certain number of moles available to actually react. You don't want to do it in molarity because, again, the molarity would be constantly changing. For example, in a titration, as you constantly add that volume, the molarity is just constantly changing. So when we go to something like part B, where we're taking our same buffer here, which is our 1 molar acetic acid and our 1 molar sodium acetate. Since it's the same weak acid, it is the same Ka value of 1.8 times 10 to the minus 5. And we're going to add 0.1 molar HCl. So in this problem, whenever you have a buffer and you're going to add something to it, either an acid or base, it is going to require an ice table. So you are going to have to do an ice table to see what the effect on the buffer is going to be. And this ice table, as we just talked about, because we're adding volume, does need to be done in moles. Now, once you do the very first ice table, you then can kind of convert it back into molarity by using the total volume. Now, in this particular example, it's a little different than most problems. We're just going to assume everybody stays at 1 liter. So all the volumes is 1 liter. So that makes the math a little bit easier. But if you had actual volumes, you will have to take that into account. So let's start with what happens when we do this. We're going to get a reaction. So we're adding HCl, which is a strong acid. Again, we have an acid part of our buffer, and we have a base part of our buffer. So when we add HCl, which is an acid, it is going to react with the base part of the buffer, which is our sodium acetate. And when that reacts, we're going to get that reaction of changing the page, come back. We're going to get that reaction that occurs, and we're going to make acetic acid like we talked about. And we'll make some sodium chloride as well. Now, we are going to have to do an ice table here to figure out what's happening. And in this case, since everything is assumed to be 1 liter, 1 liter times 1 molar is 1 mole. 0.1 molar times 1 liter is 0.1 moles of the HCl to begin with. So again, technically, even though it's 1 liter here, we're going to convert it into molarity, moles per liter. Gives us 0.1 moles. Yeah. For our acetate, again, same deal. We're going to take 1 molar times 1 liter, gives us 1 mole of our acetate. Now, also where people screw up is right here. Since this is a buffer, we actually do have some acetic acid there as well. Also taking 1 liter times 1 molar gives us 1 mole of our acetate. Like we've talked before, sometimes when you do ice tables, best not to put numbers by things you know you're not going to use. We know that this is a neutral salt, not going to affect the pH. Might as well not put a number in there that you want to use later on incorrectly. Now, again, this table does need to be done in moles because we are adding volume. Now to the change part. It is also a little bit different than we normally do. Normally here we use X to figure out what the change is going to be. But in this particular case, we know that this is a buffer. And if this is a correctly functioning buffer, which is probably a safe assumption in most cases, we should assume that this buffer should use up all of the HCl that was added. So instead of an X here, we're actually going to use a number, and the change is going to be the 0.1 moles of the HCl minus 0.1. This would be minus 0.1. And on this side, it would be plus 0.1 moles. By the way, logic tells us that it's got to be the smaller number that is the limiting reagent here, because if we took the larger number, we would get a negative number, right? And that can't be. So it's always got to be the smaller number is going to be your limiting reagent. That means when we hit equilibrium, we have used up all of our HCl. We will end up with 0.9 moles of our acetate. And also important on this side, we want to add, not subtract. We'll get 1.1 moles of our acetic acid. Any questions on the ice table here? So a little bit different. We actually do know the change that's going to occur. So we actually do use the number, and we want to make sure that we do this table in moles. Any questions on that, where any numbers came from or anything? Now, in these type of calculations, at this point, once you've done this initial table here in moles, it is very good practice to convert those moles back into molarity. So you would want to divide these guys by the total volume in this case, which again, in this case, is just 1 liter because it's remaining constant, which would give us 0.9 molar for this guy. We would divide this guy by 1 liter, which would get us 1.1 molar here. Now, it's really important, again, in normal problems, for example, we will not keep the volume constant. So in normal problems, for example, let's say you added 20 milliliters of HCl to 80 milliliters of your buffer, which means when you get down to this point and you're dividing by the volume, you would take the 20 plus the 80, and that would give you a total of 100 milliliters that you need to convert to liters to get it back to molarity. So normally, again, in a kind of a normal problem, you want to divide by the total volume at this point. I will say in reality, when you're doing buffers, it doesn't make a difference too much. You can leave it in moles, but it's very good practice to convert it to molarity because there will be a lot of calculations that you'll need molarity, and it's just good to have it in that. So if we look at our ice table, which gives us a lot of information about what's going on, again, the sodium chloride here is a neutral salt, not going to affect anything. Really, the two major things that we have left at this point at equilibrium is the sodium acetate and the acetic acid. And again, you should hopefully be able to still recognize that these guys are still a buffer. So our buffer did work correctly. We still have the buffer there when it's all said and done. And we see what we were talking about. We added acid, so we used up a little bit of the base part of the buffer, but we did make a little bit more of the acid part of the buffer, as you can see by those numbers at equilibrium. And because you could recognize it as a buffer at this point still, you again have two options. You can ice table it up. So you would need to do a second ice table, or you could just go into the Henderson-Hasselbalch equation, which will be the easier move, I'm thinking. But again, if for some reason you do not like the Henderson-Hasselbalch equation, you could do another ice table. So you may be asking, what is the ice table going to look like? The ice table is going to look like this table right here, what we did for part A. Whoops, come here. There it is. It's going to look just like how you could have done the ice table for part A. The only difference will be your initial concentration of this guy, and your initial concentration of this guy would be your equilibrium concentration from the first table. So kind of like first table to the second table if you chose to do a ice table to get to the pH. So it would be the exact same weak acid dissociation, but for your initial concentrations in that table, it would be these numbers that you would put in there. So again, absolutely, if you want to do an ice table at this point to get to the pH, you could, but probably easier just to go into the Henderson-Hasselbalch equation since you could recognize it as a buffer. So that means I'm going to do just the Henderson-Hasselbalch. pH is our pKa plus the log of the base over the acid. In addition, you should hopefully recognize as well, this is the same buffer that we started with, which means it's the same weak acid, and that means it's the same pKa value we had from the previous problem. And if we put that in there, the pH is equal to 4.74, which is what we got on the last one, plus the log of our base, and our base is our sodium acetate. And again, that's going to be the 1.1 on top. Our acid is our acetic acid. I'm sorry, I did that backwards. I'm sorry, I was looking at the wrong one. Let's try that again. Do it correctly. Take two. All right. So our base is our sodium acetate there. So our base is our sodium acetate, which is actually this guy. And that would go on top, 0.9. And our acid obviously is our acetic acid, which is on the right there, which would go 1.1. That's okay. I'll get your question in just a sec when I get a chance. So we're going to take 0.1 divided by 1.1. We're going to take the log of it plus 4.74. And that's going to give us a pH after we add the acid of 4.65. Any questions on that calculation? Again, if you did the second ice table, you would hit 4.65 as well. And you would get the same answer as which we got here. So let's talk about a couple of things here to see what happened. Looking at part A, this was our buffer with nothing added to it. So this is where our buffer started. It started out at pH of 4.74. We then added some strong acid to this buffer. And after doing our calculation, our buffer, after we added the acid, ended up at a pH of 4.65. And what we see is the buffer, the buffer kind of worked there. Our pH started at 4.74. We did not see a dramatic swing in the pH. It went down only to 4.65. So it basically was able to maintain its pH. And also a good way to check yourself to make sure you did not do any type of calculation error is we did see that the pH went in the correct direction. So what I mean by that is we added acid. So because we added acid, we would expect the pH to go down, which it did. And because this is a buffer, we would expect the pH not to go down extremely, which it did as well. It went from 4.74 to 4.65. It went down in the correct direction. Why that's important is kind of like what I did accidentally there before I erased it. Sometimes people get these guys backwards. And if you did this calculation and you ended up with a pH higher than 4.74, it should not make sense to you because you're adding acid and the pH should go down. But if you did some type of calculation, you saw the pH go up, probably means somewhere along the way you screwed up on the calculation. So again, conceptually understanding what should happen when you do these things is a really important aspect of understanding, does my number sort of make sense when I get that number? Questions on that there? Okay. Now, let's see here. I think we will stop lecturing for lecture here right now. What I'm going to do, I think, is, again, just to kind of keep us on pace, we're going to use the first little bit of lab. I'm going to do some lecturing so we can kind of get through buffers, and we'll also get through some titration information as well, which will help us with the next couple experiments that are coming up, kind of starting next week. So again, to kind of keep us on pace, I'm going to actually lecture a little bit at the beginning of lab today. So we'll take a break. We'll start lab at kind of normalish time, 11:30, 11:35. We'll do some lecturing continuing on here so we could kind of, again, keep on pace with everything. In terms of labs and everything, you do have a lab report that is due today, I think. Yes, officially it's due at 11:30, but I think you have until the end of the day to upload it. So make sure you do upload it, that equilibrium lab. Again, a reminder that the pH and hydrolysis lab has been up since the beginning of the week, so you can be working through that. You should, at this point, from what we finished last time, or even before that, you should have enough information to complete that lab. So that's going to be due down the road, I think, next week maybe, or the following week. And we're going to be rolling into next week officially buffer lab, which is where we're talking about now. So that's why we're going to continue to lecture to kind of keep on pace so we could kind of start that lab, and titration as well will be coming up after that. So we'll take a break. We'll start about 11:30, 11:35. We'll do some lecturing for a bit for lab. And then at that point, you could go off and continue to work on the pH and hydrolysis one. So let me just look at your questions real quick before we officially end. So to convert to moles, to convert the moles to do the ice table, remember you need to take the liters times the molarity will get us moles. So you need to multiply it to go like here. And at the end, to calculate the molarity, you need to take the moles divided by the liters will get you the molarity, which is what we did over here. Yeah. So yeah, you do need to do that. And then again, at the end, it would be the total volume that you would do. Okay, so we'll take a break. We're going to probably continue lecturing. We'll talk a little bit about the pH and hydrolysis lab. I think it should be pretty self-explanatory. You have a bunch of salts that you have to sort of write hydrolysis reactions for and kind of figure out the pH. So we'll kind of go over a little bit of that, and then we'll continue lecturing. And then, like I said, you could go off and kind of work on that stuff if you like. And we'll start up again about maybe 11:35-ish. All right, any other questions? I think I got everybody. And like I said, officially the lab report's due at the start of lab, which is the 11:30 due date. I think you have, again, until 11:59 tonight. Technically, it would be late at that point. I'm not sure I'm going to mark it late, but technically it would be marked late, but you can still upload it. All right, I'll see everybody in about 20 minutes or so. Get up and stretch, and we'll continue on.